Great, so let's get started. So welcome back, everyone. So we are going to talk about cross-validation today. So this is not going to really, well, it's like something you can kind of think of it now. You kind of think of this, so it's like an algorithm, but it's not really an algorithm in a traditional sense where we're going to kind of so set up some problem objective and then solve that objective. But it's kind of an important way of kind of how you evaluate how well your regression or your learning algorithm is so actually working. And it's kind of different like fundamentally different from what you will learn in like a statistics course. So if you learn in a statistics course how to validate how well something is working, or whether something is working, or whether something is interesting, there's a lot more modeling which is implied in this. You have to choose the right model in order to evaluate it. With cross-validation, it's kind of helping you choose what is the right model, or evaluate how well your model is working, but does not depend on the choice or the decisions in the model. It'll work with any sort of model. So it's kind of so I'm not entirely sure of like the full history of cross-validation, but it's kind of slowly been this revolutionary paradigm shift from like traditional statistics, which are about 100 or so years old, to what is used in most of machine learning and data mining to say how well is something working. And it's kind of really, so it's kind of this really important idea. So that's what we'll talk about today. If I thought, so important, if I thought it would have been appropriate, we could have started the whole class with this idea, right? It's that important, but I think it's easier to talk about in the context of regression now that we understand how regression actually works. This will make much more sense. So before we dive into the details of the lecture today, let's just review some stuff on the schedule. So the good part of the schedule, this is the last week before fall break. So that's exciting always, although I'll miss being here. Hopefully everyone finds some other interesting stuff to do with your time, whether it's catch up or kind of take a much needed break. It's nice to have actually fall breaks in the schedule again. So importantly, homework 3 is now out. Okay, homework 3 is not due until after break. It's not due till the week after break. So you have some time to work on this. I would suggest trying to start on this before break if you can. I know there's sometimes a lot of stuff kind of scheduled right before break, but trying to have a look at it. It's a bit a little different than the other homeworks in that you're actually going to be working with some actual data. I've uploaded a few small data sets, which you can download, and then you're going to actually run regression on these data sets. You're going to actually do polynomial regression and evaluate this stuff. This first question, which is half of the points, you should have everything to start working on this now already. Question 2 is going to be mostly about the lecture today. And so that one you'll also be able to start working on. Question 3 is going to be on the basics of gradient descent. This will also be a more implementation in Python question. This one will be a little bit harder to start on now. We will not cover this material until after break, but you can take a look at it. It's going to involve gradient descent, which is the topic here, and there's going to be some code, and it's going to be kind of get that code working with these other examples, and then kind of apply this code just to get this as like a kind of introduction to gradient descent. Okay, so it's a little different if you're very familiar with Python, then this probably is not going to be super challenging. If you have not worked much with Python before, this one there'll be some learning that you will do in the process of doing this. Part of this involves loading some data sets and doing some basic working with data. And I've linked a tutorial that I had a TA give last year, and which was recorded, so it's online here. This main link here, the Python tutorial on loading, etc., is a video in YouTube, and then the Python notebook, the collab notebook, is also linked there. So if you're not familiar with how to do that, there's a bunch of resources there on how to do it. It's not terribly hard, but there's kind of, if you're doing it within Colab, you have to kind of get the file in the right place, and so, it just takes some getting used to, and so it's all kind of laid out there. All right, yeah.
Just to clarify, we don't have to do Colab, right?
So it's not required doing Colab. If you're familiar with, if you have Python loaded on your system, you have PyCharm or something, you're welcome to do that. I try to make this class self-contained within Colab, and so all the instructions are that way. But if you have your own kind of IDE set up, or you do it on the command line, like I did before I discovered stuff like Colab, then doing that is also fine. So okay, great. So I'm just kind of trying to give you a bit of a warning that homework 3 and homework 4 have a little bit of implementation, and they're kind of different from the first 2 homeworks, and that those involve some element of review. This is all new material, so they might take a little bit longer. So please kind of don't delay too much in working on these at the last minute. Even if you could finish the first 2 homeworks at the very last minute pretty quickly, that might not be the case for the next 2. So just kind of FYI on those. But hopefully they're designed to kind of force you to learn the material. So I think they're so worthwhile doing. Great. Okay. First thing, the other thing is the quiz is going to be on Thursday, right before fall break. In class, get your cheat sheets ready and so forth. It might cover a little bit from the last lecture of linear algebra, the day of the quiz, and it's up through the regression, the stuff in the lecture today. Okay, so the standard sort of thing for the quiz, it'll be on Canvas. You guys should all be pretty used to how this works at this point. Again, it'll be the last part of the class. At that point, you can I'll be here or on Zoom to answer any questions. So I recommend it then, but it'll be available until the end of the day. And then Thursday we also have a little bit of slack in the schedule. So far, there hasn't been anything really important that I think we missed that we need to go over. Probably if it was my choice, I would probably go through the start with why is that kind of linear algebraic expression for linear regression, why is that the right solution? Go and explain that. We can also just do a review of the linear algebra section we've done before the quiz. That might be helpful. We could also talk about some ethical issues with regression and some other stuff. If you have a preference for what to do on Thursday, please, you can let me know either now or over email or kind of on Canvas or on Thursday, or I'll just kind of talk about what I think is interesting then. Great. So okay. So that's now a hand up, just resting pose. Okay, great. Just wanted to check. Okay, let's get into the lecture. So, so cross-val, all right. Okay, so cross-validation. Okay, so this is, we would like to understand kind of basically, let's think of how well is regression working? Right, so this is kind of the big question. How well is the regression model that we built actually working? And kind of a similar question of kind of one of the things we learned in the last lecture was that we could take, for instance, we could go and say that the input was kind of, let's say, x, y, where x and y are both in Rn, and we could then convert this x into this x tilde p, right, where this was 1 x1 squared up to x1 to the p, 1 x2 squared up to x2 to the p, and so forth. Expand this, do this polynomial expansion into this matrix. Okay, and then for each of these, I could solve an alpha star p, which is, this is going to be this p-dimensional matrix, where I do xp tilde, transpose xp tilde, inverse xp tilde y. And I know that this gives me the optimal model of the form, right? If I get a model alpha p of the form x, which is equal to alpha 0 plus alpha 1x plus alpha 2 x squared plus alpha p x to the p, right? This alpha p star, remember this is equal to alpha 0 up to alpha p, right? This. Okay, so if I'm restricted to this form of a model, this polynomial form of model, this is the optimal choice of how to choose the model parameters to minimize the sum of the squared errors, right? So this is what we talked about at the end of, at the second half of the lecture on Thursday last week, right? So this minimized the sum of the squared errors. That's what, when I put the star up here, that means it's optimal in some way. Okay, but one of the things that I said is you can do this for any value p, right? I can do this for any value p here. This p is a choice, and this is optimal if I go up to this pth term in the polynomial sequence here. Okay, so the kind of another question is which choice of p? How do I choose this parameter? How big of a polynomial, what degree polynomial should I be using to try and fit this data, fit a model that matches this data, right? So how am I supposed to choose this value of p, right? And so if we go and if we think about some actual data here, right? Let's look at some potential data. All right, so this is a value x, this is a value y, and then I'm going to have some actual data points, right? Each of these, this might be xi, yi. Remember, this is the x value and this is the y value, right? So if I have a data point here, I want to fit a polynomial through here. If I I set, this would probably be the optimal line associated with alpha star for p equals to 1, right? If p is equal to 1, then this is a line, then this this L is L of x equals alpha 0 plus alpha 1 x, right? So this is how I predict this. I set this equals to the value y, right? Or this is my y hat, my prediction of the y. This might be the optimal solution for p equals 1, but if I can do p equals 2, then I can probably do a solution that looks like this. This would be alpha star for p equals 2. This would be a model alpha 2, which for some x might equal alpha 0 plus alpha 1x plus alpha 2x squared. And this would equals my y hat now. Now it can be this parabolic function. Okay, but if I choose alpha equals to 3, then maybe I can get a function that looks like this. This might be alpha star alpha 3 star, right? So this would be, now it can have 2 terms in it. If I have a degree 3, this is fitting the data a bit better. And I can keep increasing this. For instance, if I go up to, I could think I can get let me move one of these data points just a little bit here. Okay, let's see if I go. Okay, this might be the answer for, say, alpha star for p equals to like 7, right? If I said p equals 7, I can actually get a curve that's a polynomial curve that goes through exactly all of these data points. Okay, so this curve is going to have that this sum of squared errors of x, y of m alpha 7, right? This will equal to 0 because I'm measuring all of these errors. How far, again, in the vertical distance is every data point away from this curve? And the answer is 0. None of the data points are off of the curve. I get 0 error here. Okay, so this, so if I keep increasing this p, I will eventually get no error on the data. Now, this might seem like a good thing. In fact, kind of fitting polynomial functions through data points is used in like this was the foundation of a lot of CAD modeling when they first were making things like the hoods of cars, that they wanted to make them look kind of smooth and shape. They started with ideas like this about these, how can I can describe a curve by moving these data points, and it gave them an interactive way to design these hoods of these cars. Now with like it's like the Cybertruck, I guess it's all like polygons and stuff. But you know, back in the day, this was the cool way of modeling cars and parts, and actually the CADE lab. If you ever, hopefully a lot of you go to the CADE lab, that's based on computer-aided design and engineering or something. And so that was based on, Utah was kind of one of the leaders in this design of models using these polynomials and other generalizations of these ideas, where I want to fit through all the data points. But my goal here is to build a model that is representative of the data, and this is not necessarily a good answer, right? What I would like to do, I would like to think of this instead of, well, how good does it fit the data I have? But if you remember back to the first lecture we had on regression, the real goal was when I had some, let's say I had some other data point. I have X, let's say X new. When I just have this other data point and I want to try and predict what is the value, going to be, right? Each of these gives a guess on the Y value based on where this X new, if I look at the function that I create, what Y value does that function get, right? So that's what this is used for. I want to build a model so I can predict the value of new data points. Remember, I had there were those customers on the website, and how long did they spend on the website, or how much did they scroll or jiggle the mouse? That predicted how much they would spend. That's what I want to do. Or if I have someone's information about someone's height, I want to predict something about their weight. Well, that's what my goal is here. Okay, and this orange model with p = 7 does a very good job on the data I have, but it might not do quite as well on new data here, right? It's giving you a much lower value than all the other kind of estimates I'm getting in this case, right? So this isn't generally doing good on new data. And so the question we want to ask is, how well does the model M generalize to new data? Okay, so I want to think about how well it generalizes to new data. That means if I get new data, how well is it going to do on this new data? All right, so if I just had this data and I built these models, which one do we think is going to generalize to new data better? Yep. So number 3, the green one here, right? So this green one is kind of nice. It's fitting pretty close to these data points here. This part seems hard, but it's not doing quite as well there, but it's doing pretty close in general. Yeah. So why do you like number 3? Okay, so it's not dropping off as fast anywhere. Great. So the dropping off, do you mean like outside? So if I extrapolate outside the data I have, it's not dropping off as fast. That's usually a good sign, right? I might have another data point pretty close to the data points I have. That would not be unreasonable. And so it's not kind of changing very quickly right when I get outside my data. You typically, if you're looking at these one-dimensional problems, you're often hear things, you don't want to extrapolate beyond the data you have, right? And so going outside of here, and if it drops off, well, that might be extrapolating. But actually, when you're in high dimensions, the notion of extrapolating is kind of much harder to gauge what is interpolating versus extrapolating versus what's inside your realm of your data, what's outside. Turns out most of it is kind of outside what you'd say is the convex hull of your data. So kind of, whether it would do good to extrapolate a little bit, that's, whether it drops off quickly or not, that's probably a good thing to look at. That might be how steep can the slope be at any point in the model. You don't want to be anywhere near the data. You don't want to have a very high slope, for instance. That would correspond, for instance, with if I change the X value, because there's a little bit of noise in it, is the Y value going to change very quickly? That's sometimes seen as something which is not very good. There are regularization terms that if you keep reading in this chapter in the book, you'll get to that will help kind of fight against kind of these very high slopes. So that's kind of a good property. Does anyone else like number 3, or they have a different preference or a different rationale? Yep.
Aside from dropping off even from just looking in that range of data, it's less, it's more resistant to
Yeah, right. So it's more resistance to noise in the data. Do you mean by noise? You mean
perhaps like I guess we don't really know the underlying function for this, but perhaps like a lot of this data points are just random deviations from the actual.
yeah. So these data points might have some random deviation from their actual value, and this can mean so two things. One is this x change, small changes in the x value that we talked about. And the other is, well, maybe I don't trust them that much. If you remember, for fitting the one-dimensional function, the blue one, we assumed, we talked about that we had this assumption that the y value was equal to some L, some line plus some noise. And we didn't know, we assumed maybe we could model this as Gaussian noise. We didn't know how much there was, but that was talking about, well, there's some y value noise, right? So it might mean that each of these is actually, there's some interval of trust here, that it falls in some range here in the y values. Maybe those blue one you can't see very well. Let me try. Right, but maybe I don't know it's exactly that value, but I say, well, it's probably somewhere in this range here, not exactly this, right? And if that's the case, then I shouldn't worry too much about hitting these points exactly, but I should try and be close to them, right? And if I'm somewhere close to them, that's probably that's probably like sufficiently good, right? I don't need to hit them completely kind of numerically down to 8 digits of precision, but maybe even like 2 or 3 digits of precision is might be okay, right? Or I can think of a range on each of these, or a probability distribution, a normal probability distribution on the value. And if I hit close to that normal probability distribution, then that's probably good. I guess I drew these so they're a little bit outside the range, but so maybe I make these a bit bigger, and then they intersect kind of each of these models, right? And then each of the models is kind of going through this range in some way, right? I'd still like to be closer to the data points, but maybe there's something I'm sacrificing, right? The slope is high if I'm getting too close to them. To get too close to them, I have to make the slope so high. Okay. So there's often a notion that was kind of, anyone have any other thoughts to add? Yep.
That's just a general question. So here, t equals 3, t equals 2, as far as within the data set, it's almost the exact same curve, the green and the red. Is there any reasoning why, if that happens, you would prefer one over the other, if within the data they're making the same shape?
Yeah, right. So yeah, so what is it? In the data, the red and the green, which are the second degree and the third degree polynomials, are almost the same on the data, right? And this is quite reasonable in this case here. So if you knew that they were the same on the data roughly, then is one better than the other one, right? Right. So if you were thinking this from like an algorithm's efficiency point of view, and I need to evaluate the function, right? Well, the one with fewer terms is a little bit faster to evaluate, right? So not that much faster, right? It's 1 extra terms, some extra multiplies, but it's a little bit faster. Really, the kind of the main thing people think about, well, this does come into play. Is it, can you evaluate it faster? Main thing is that the green, the red one here is like a little bit so simpler. Okay, you'd like to keep the model as simple as possible. Okay, there's this thing called like, so Occam's razor, which is kind of so often called or often referred to as like, so keep it so simple, stupid. Like keep your model as simple as you can. That explains the data. Okay, and so the 2-degree model is simpler than the 3-degree model. I didn't even write out the 3rd-degree model because it would have had more terms, and this is already kind of cluttered. Okay, so I'd rather have a model which is so simpler. Okay, so let's say what makes a model good. We had ideas like it is stable to noise, and this could often be in the x coordinate. It is going to be fit the data well, but with so some noise tolerance in y often. Okay, and then we want to make it as simple as so possible. Okay, so I mean, the first thing we often think about is this. So the second one, this 2 here, we want to fit the data as well as possible. But then given that, we can kind of break ties or kind of relax this a little bit, right, by allowing noise and say, well, we'd also like it to be stable in the x coordinate, and we'd like it to be as simple as possible, right? So these are kind of intuitive things that we would like to see. But the real question, these are intuitive properties. The real question is, how well does it generalize to new data? Okay, we'd really like to question, how well is it generalized to new data? Yeah, that's a question? Yeah, so we want to be stable to noise in the x coordinate. That would be like if I move this x coordinate a small amount, I want to know how much does it change the y coordinate here, right? So in the blue model, for instance, the 1-dimensional, the 1-degree polynomial model, if I move x a little bit, I know it linearly shifts depending on the slope, the alpha 1 parameter, how much it changes this y parameter, the y value. But in the orange model, it actually can change much faster. A small change in x can have a very large change in y. And that's typically viewed as not being very good. Yeah, great. Yeah, okay. So these are intuitive things we would like to be true, and we can use this as kind of a guiding principle. But really, the goal is, how well is it generalized to new data? How would we evaluate how well it does that? I mean, it could be I came and I gave you more data points, and they all fall exactly on the orange model, which seems like it's too wiggly if I have only these 7 data points, or yeah, these 7 data points. But if I had 100 more data points and they fell exactly on the orange curve, well, then it would have done very good, right? Or if they fell exactly on one of the other curves, then that one would be good. But I don't have necessarily new data points here. So how do I tell how well it does? A model does would potentially do on new data points I don't have yet. Okay, so this is where cross-validation comes in. Okay, and this is predicated on the idea, assume that my x, y are drawn IID from some unknown kind of distribution. Here, let's call this, say, phi or something, right? So there's some unknown distribution that the data is drawn from. Okay, and so this means that each data point is kind of like a random sample from data that I'm going to get from, and that new data, let's call this x prime, y prime, would also come IID from the same distribution. That the new data should also come from the same distribution. This is, I only have this is x and y at input. I don't have the new data yet, but I assume it will come from the same distribution as the data I do have. Okay, so I assume the data I do have comes from some distribution, IID. Each one is a random draw from some underlying distribution. Okay, so what I'm going to do is I'm going to use my data in two different ways. I'm kind of going to assume that, you know, this picture is a little deceiving in that I only have like 7 data points here for an illustration. I'm going to assume I have a lot of data. Okay. Also assume that that n, the number of data points, is so large. Okay, so I have a lot of data points. This is a technique that partially why it wasn't used much in early days of statistics was they didn't have a lot of data back then. They had to collect it by hand. You know, people were running experiments on plants, and they had 7 plants that they could run, or 7 species of some bug that they had collected. Now we can go and kind of scrape some data off the web and easily get, you know, hundreds or thousands or millions or hundreds of millions of data points there. We have a lot of data. Okay, so this is perspective when you have a lot of data. Okay, and now what we're going to do is we're going to randomly split x, y into a training set, and we'll call this x train, y train, and a test set, training set, and the test set, x test, y test. Okay. All right. Well, once we do this, we're going to split it in these 2 ways, and we're going to train a model on the training set, and then we're going to evaluate how well it works on this test set. Let me break this down a bit more. Let's think about, I like to think about the data. Again, we have this table where we have y, we have x. Okay, and we're going to split this randomly by, so I'm going to pull out some random lines here in this data set. These are all going to go into, this is x train, y train, and then I'm also going to pull out everything else that wasn't in the training set is going to go into the test set. Okay, and so this is into the test set. Okay, I like to draw it this way for a couple of reasons. I think it illustrates important points. One is when I pull out an actual data set, an actual data point, right? Let's look at this data point here. This is xi, yi. Well, this guy then winds up, this guy, this is xi, yi. The x and the y stay, so stay paired together. Okay, so I draw the explanatory variable with the dependent variable, and I put them both together here. And second, it's random. So I randomly select rows to put in one or the other, right? So I don't just take the first set and put them in one and the second set put them in the other. I do this at random. Yeah, question. Yeah, so it varies, and I'll come back to this and give some insight. It's usually, I'm gonna want to use this space. I'll say usually either common ones are 70% train, 30% test, somewhere in there. Sometimes 2/3, 1/3, or maybe 90% train, 10% test. These are pretty common. It's kind of a trade-off between the more data you put in your training set, the better the model that you train is, but the worse your evaluation of that model is. Okay, so it's kind of a trade-off. How many, and so I would kind of dictate it by make the train set as big as you can, but so you can still have enough in the test set that you think you get a good evaluation. Okay, and how good is your evaluation? Well, this is IID data. You're computing an average. So you want to apply, the test set is as good as like the central limit theorem says it is, right? So, and we had bounds like the Chernoff-Hopting bound or Chebyshev bound, that if you know something on the bound of the data or the variance, you can estimate how accurate your test set evaluation is. And so if you can look at that and say, how much do I need to trust this based on how much variance there is? And I'll put the test set as big, just as big as I need to evaluate, and everything else I'll put in the training set. The more I train on, the better model I get. Yeah. So that's how I like to think about it, but these are common. And okay, yeah. And for instance, in your homework, we're going to give you a training set and a test set, which is we told you which way to do it. That allows us to, I think this allows us to kind of grade it more easily. That way we know what the answer is supposed to be. But in general, you should kind of randomize this in some way. Yeah, great. Okay, so I do this split here. Okay, once I do the split, then I need to do a training. Okay, and I'm gonna think of this as alpha star on train is going to be equal to x train transpose x train inverse x train transpose y train. Okay, so I'm going to use the training data. Kind of one is to split, two is to train, and I train on the training data. So I just use the data in X train and Y train to build a model. Okay, and in regression we build the model like this. Okay, and then step 3, I want to evaluate, and I do this by the sum of the squared error. Okay, but this is now on X test, Y test, but alpha star on train. Okay, so this guy, let me highlight these, right? So this is training data, and I get out this model that comes from training, but the evaluation, the input to the evaluation is on the test here. Okay, so if I write this out, this is equal to sum over x, y, and x test y test, right, over again, y minus the model alpha star train on x here squared, typically, right? So again, this is on the test, right? So these guys are from the test set, but this model here I'm using to evaluate is based on the training. Okay. Okay, so now I'm evaluating on the testing data, and that means that the reason this works is because I assumed that there was some underlying function that IID was generating this data. That means that both the training data and the test data, because I split it at random, also was IID from this same distribution. So both of these were IID from the same distribution. So now I can evaluate on the test data here as if it was new data. It's new from the perspective of the training data. It was not used in the training. So I'm saying, how well does this work on new data? Well, this test data I've held out looks like some new data, right? This looks like some new data. So if I were to get more data from the same distribution that I haven't seen yet, that wasn't in my initial input, well, then I would expect it to perform so in a way that's similar to the way I've evaluated the error. Expect the model to perform so similar. Okay, and if I have enough training data, kind of at some point, the choice in the model parameter, right, the value p, for instance, that I chose, it's not going to really train a much different model here. There's going to kind of be the same model if I put more and more data in it. The modeling is what's called so consistent that if I put more data into the training set, eventually it's going to reach the same model. And depending on this parameter p, for instance, and then I'm going to kind of see how well it does on the test data. I'm going to say this is how well that choice of the model parameter worked. Okay. All right. Okay. So okay. So an important question, and I said, I started with how well does this generalize to new data? Okay, and then we came to cross-validation, but I'm going to kind of twist this around and I'll have slightly different answers. What is cross-validation good for? Okay, so what is cross-validation? What is this good for? And kind of what might be surprising is that there are two different things that we have been discussing this is useful for. And there are two separate things, and you should kind of keep them so they're separate. Okay? And turns out you can't do them at the same time. So that's why it's important to keep them separate. Okay. The first thing is so predicting how well does the model do on new data. Okay, I want to predict how well this model does on new data here. And in particular, if I want to think about this, I don't necessarily want to use the sum of squared errors. I want to use like the average, or actually the root mean squared error. So I might want to use like the root mean squared error, which is going to be, I'm going to start with the xy over the x test y test, right? And I'm going to look at y minus m alpha of x squared, right? So this is what I had before, but the root mean squared error, this is the root mean squared error. This is instead, I'm going to put a 1 over the size of x test, right? The number of test points I have in front here. It's like 1 over n. So now it's an average. This quantity is a average squared error. Okay, but this is not so useful. Tell me the average squared error, which is the different units from my typical error measurement. And then I'm going to take a square root. So the root, now this has the same units as the original y coordinates, right? Because I've taken I've squared stuff and then I've taken the square root. And it's kind of an average. And so this gives me some prediction on about how well it does on new data, right? This, and I think sometimes we won't talk about it with the square root, and that's just the average squared error. So the mean squared error is also sometimes used. So this would be the mean squared error, just the purple part inside of the root. And this is also useful for predicting how well does it do on new data. How well does it generalize onto new data? So I build a model. I want to say, okay, here's my prediction, but I also, say on average, I have about this much error. So that's kind of how much I trust my prediction. So I don't just say, okay, if you have this, height, this is how much your weight is. That's not going to be exactly right. It's going to be that with some error to it. Okay, and this gives me a sense of how much is that error. It doesn't assume anything about a model. It just calculates as the average squared error, or I could do the average absolute error if I wanted to, but I somehow can measure the the average error in some sense. Okay, so this is one. The second one is to choose the best so model, or for instance, the model parameter, e.g. kind of this value p. Okay, the second thing is to choose the best model, right? And this is slightly different, right? What I can do is I can evaluate, say, the mean squared error for x test, y test on m alpha 2. Let's say I didn't know if the so I have a model which is based on a second degree polynomial, right? Or versus the mean squared error on x test, y test for a m alpha, let's say 7, right? So I didn't know the 7 one gave me kind of 0 error in my training data, but the 2 one might generalize better. So I compute the evaluation on the test error based on models I've trained on the training data, but with 2 different parameters p, right? So if I want to know this parameter p, it could either be a 7 or it can be a 2. I want to know which one is better. And I can evaluate on the test error, and I can say which one did better on the test error. That's more likely to do better on new data I haven't seen yet. Okay, and so these are slightly different from each other. And in fact, you can't do them at the same time. You should not do them at the same time. I could do that. I could first choose a model, and I say, okay, the model with parameter 2 is better than the one with parameter 7. And then I say, well, then I can use this mean squared error to say about how well I expected to do on so new data. This is slightly broken. I'm using the same idea of back here where I fit all of my data with the training data because, well, the choice of 2 versus 7 was actually part of the training. That's part of an algorithmic choice of how I got to choose a parameter. I could think of alpha values as being the only parameters, but this value p that described the complexity of my model, and there are other ways to add these other parameters in here, is also a parameter that goes into the choice of the model. And so I'm using the test data to determine this parameter, and so that becomes part of the training step. Okay, so I will do slightly better here on mean squared error than I would on fresh data. Because this is it. Let's say I did instead of 2 versus 7, 2 versus 3. And they're about the same, right? Remember, 2 versus 3, they're almost the same here. And so I'm going to end up picking the one that's doing slightly better on the test data. But that slight better may have been from the random variation in the data. And it's not necessarily reflective on the actual data I have. So I can't use these values. I cannot use these values to predict how well it will generalize. It's slightly biased. It's slightly optimistic. Okay, if I want to do that, if I want to do that instead, I will split the data, my x, y, into kind of these 3 sets. I will have the training set. I will have the kind of so somebody will call this the dev set. So and then I'll have a third set, which I will call the evaluation set. Okay, and I split my data randomly into these 3 kind of components. Right, these are going to go into here. The blue ones are going to go into the dev set. And then I'm going to have, let's see if I have, okay, these guys are then going to go into the evaluation set. Okay, I split it this way. I can then, this one is to build the model. This is basically through some optimization. Okay, and we can use that linear algebra stuff, or we'll see gradient descent to do that. This one is to choose the the parameters. Okay, and this one is to evaluate generalization. Okay, right, and these are choosing the parameters and evaluating generalization are 2 separate things, and you don't want to mix them up. All of the top part here, all of this is part of the training. Right, this is all part of the training, and the evaluation is just below there. Okay, now not always do you want to actually do both, and then you only need to do 1 split, and that's the most common thing, that you only need 1 split. But if you are going to do both, then you actually need to do 3-way split. Yeah.
So basically, you're comparing 2 models that were trained.
Yep, that's right. Yeah. Otherwise, you're going to yeah, if you have 2 models trained on the same day, you need a completely different set to compare them. That comparison happens here, right? The evaluation set is kind of how well you expect to do on some new data. Sometimes you could have multiple rounds of choosing parameters, or choosing a type of model, polynomial regression versus kernel regression, and then you have even more, potentially more layers here. complicated. This comes up in like these like Kaggle competitions. Has anyone done everything on Kaggle? It's this website that has a bunch of kind of challenges with data. Say, how well can you do? They will often give you a training set. They will allow you, if they set stuff up correctly, they will allow you to kind of ping the server with models and say, how well does it do on this dev set? And they will reveal the answers to you. And this will have a leaderboard. And if they do it correctly, they've held out a third set at the end where they take the ones on the leaderboard and they actually evaluate it. If not, there's some tricks you can play to actually learn the dev set by probing it with models, and you can overfit to it. But if you do new data, you might actually do poorly on it. And people have done that on some of those. So kind of the ones that do this properly split it into 3 things and don't reveal the evaluation set until the end of the contest. Okay, cool. All right, so how are we doing? All right. Good. I want to go into an example now on Colab, where we can kind of see a little bit this in practice. Okay, and this is, let's see right here. Okay, I should have already opened it up. Okay, let's walk through this. We're going to start with, we're going to load NumPy, linear algebra package. We're going to do some plotting. Okay, I've got some training data and test data, and I've split it. I've already split it here just for this example. So I haven't done the randomly split. Assume these are randomly split. It's got X and Y, and I've kind of just kept them separate because that's how we'll pass them into my algorithms. And I'll plot them here, and we'll see. Once this loads, that it's going to plot the training data in blue and the test data in green, right? So now we can kind of distinguish these a little bit. And assume this was split at random, and then we can, well, let's start with 2 here, and we'll fit a 2-dimensional model. We'll again use this polyfit function. It's easy for these things, and we can calculate the, now we can, so we fit the polyfit model on the training data, right? Only the training data showed up at this stage. And then we calculate the error, the residual, the sum of the squared errors, right? This was just on the test data, the one with the E for test, I guess. And so just passed in the difference of how well it fits versus the actual values we had. And we have the residual. I had 3 points. So the residuals on those 3 points were 0.07, 0.8, and negative 0.51. Okay, I guess this is backwards from how I did the residuals before, in the book and stuff. But okay, but then I can write the when I take the sum of the squared ones, it's not going to matter. The sign doesn't matter, and I get a 0.91 is the sum of the squared errors. Okay, that's for 2, but it's also helpful just to plot this and see what it looks like here. All right, the suspense. Okay, great. So there we see the plot, and you see with the degree 2 fit, it looks like it passes through the blue data pretty well, and also the green data. This seems like a pretty good. The testing data in green, it looks like it's getting some error, not too different than the blue error, but the blue data points is passing through closer on average than the green data points, because those were in the test data, right? So, okay, if I were to go, I can go back and change value 2 to 3, rerun the data, recalculate the residual. I'm 0.93, I was 0.91 before, right? So it's a little bit worse error, but roughly the same. This was similar to the example I drew on the slides. And okay, and it looks, again, it looks pretty similar. Probably once it's off to the right of the screen, it curves back up again. But Looks like it looks like a quadratic part here. Let's change this to 4. So see what happens when we do p equals 4. Let's see, okay, so the fit on the actual data is going to be better, but on the test data has actually gone worse. I now have 3.2 arrows, about 0.9 before. Now on the test data it does worse. And let's look at why. Yeah, so look on these 2 data points, the 2 data points on the right in the middle, it's doing pretty well, maybe even better than before. But the one on the edge, where we were kind of how fast it dropped off, like you were saying, it's really suffering there because it's dropping off too quickly. Okay, and so I'm getting worse error with a fit of 4, even though it's probably doing even better going through these blue, the training points. Okay, and let's crank this up to 8. See what happens. Let's see if I can fit this. Okay, on 8, it said, again, it said, okay, there's some sort of warning because I'm fitting too, I'm probably inverting. It has to use some tricks because I wants to invert a matrix I shouldn't have inverted. And let's see what happens here. When I do degree 8, again, the error is worse. I get 15 instead of 0.9, so much worse sum of squared errors. We see, look, it's really going through those blue points very accurately here, but at a much worse expense of the green points. The one on the left has really dropped off quickly, and also the one on the right that was in the middle before, that one shouldn't have been too bad, but because that polynomial decided to take this curve to make it sure it really went through the training points well, it's really doing poorly on that other test point, right? And so this is kind of what can happen, right? And so that's why using these held out test points are can be a more effective way of choosing the model. They're much better at saying, you know, how well this is going to work on new data. Again, you know, the P2 one is probably what I would, let's do a P1 fit here. A P1, a linear model would be an even simpler fit. This is getting an error of 5 here. Again, this is worse again, right? So when you have 5, the model seems, you know, it's a much simpler model. And now it's actually, it's not hitting the training points as well either. It's missing 2 of the training points. 2 of the test points it does pretty well, but it again misses to the high side on this testing point on the left here. And so what's happening here is the model is not powerful enough to fit the actual trend in the data. So you can underfit. So this would be kind of what you call like underfitting the data. Whereas if I did a p equals 8 or even p equals 4, I'm overfitting the data. I'm fitting too much to the training data, so it's not going to generalize as well. And so this choice of 2, let's go back to what we think was our best model. This had slightly less error than 3. Good, slightly less error than 3, but it's also simpler, right? If I have a choice between 2 models with basically the same generalization error on the test data, I should probably predict the one that is going to be. I have some kind of race conditions here. Okay, so I'd probably choose the one that's going to be simpler. Okay, great. All right, so see how, yeah, this kind of looks like it really fits the trends of the data. It's going up and then it's leveling out and curving off. This seems like a good kind of intuition of what's going on here. It fits the eye test and also the kind of the sum of squared errors on the evaluation data also kind of is tells us this one is the best.
So there's a question, is there a function that tells the most optimal p to use in the chat?
Oh, okay. So yeah, so is there a function that says the most optimal p to use? If there was one function in this example here, it would be this function, the sum of the squared errors. I would just use this, right? I'm evaluating the sum of the squared errors on the test data. That tells me And I can do that for every value P. And that's going to give me the one that minimizes that is the one I'm going to use. That's what I'm going to tell you to do here. But there's not like a closed form function here, right? I don't have this magical solution. I can say this is the best value P. In fact, maybe I could think of a P point, 2.2 or something, right? That's is not an integer. Maybe that, it's not like that, right? This is a discrete choice in this case, and I just try all of them. There are, and you kind of need to just test all of them. It's usually fairly convex. As you get further away, either too small, you tend to underfit and it keeps getting worse. As I get too large, it tends to overfit and it keeps getting worse. It tends to be looking kind of in the shape where there's a single minimum, but that's not guaranteed either. There's nothing to guarantee that. It's just kind of, it's random data. So it might be that there are two kind of equally good things like P equals 2 and P equals 4 are both good, but P equals 3 doesn't work for some reason. That's possible, but and then in that case, you choose the one which is simple. So you can start with the simple model and work your way up until the test error tends to start going up, and then you can stop. That's what I would recommend doing. Okay, great. Oh, why do you use sum of squared errors instead of root mean squared error? Yeah. Okay, so this is a good question, and I'm going to go back to my slides here and say a couple of more things. So the thing is, what we basically want is the arg max of P of kind of what I did here is the sum of the squared errors of X test Y test of M alpha P, right? So this is what I did here, right? This is a function of P if the X training data and the testing data is fixed, and I solve for alpha as a function of the training data. And I want to, I don't want to maximize this. I want to minimizing this. So I want to take the arg min and I'll call this P star. The arg min. Now it turns out this is equivalent to the arg min P of the root mean squared error of the same. So if you remember our arg min function, right? This was I want to return the argument which minimizes that expression. The difference between these two is one is that this root mean squared error is actually equal to the square root of 1 over n, which is the test size of the sum of the squared error, right? So the 1 over n does not change, which is the max, and the square root also does not change, or the min. The 1 over n does not change, which is the min, and the square root does not change, which is the min, so I can use either of these. So the root mean squared error is a little bit easier to interpret. The sum of the squared error is easier to calculate because I don't have to divide by n or take a square root. So I'll calculate the sum of squared errors, but I might to choose the best model, but the root mean squared error is easier to interpret what is actually going on here because it's in the same units as the y. All right, okay, let me say one more thing here. Sometimes, so what to do with not enough data to split. Okay, so there's some kind of people here in the computer science department who do research on these things like these, on like the imaging in brains that before and after someone gets into like some sort of car accident. They want to know what has changed structurally in the brain. As you can imagine, in order to do this, you need to get an MRI a little bit before the car accident and one afterwards, and you don't plan on getting in the car accident. So they don't have a lot of these data sets. They have like 5 total images of this, right? So in that case, the number of data points you have is not very big, but I'd still like to use cross-validation to evaluate models. That's kind of an extreme case. That's only 5, but imagine I really wanted to train the best model possible. I think it's a complicated model. I'd like to have a larger value P, but in order to train a larger value P, I feel like I need more data to do that. The more complex model, the more data I should have. So how do I balance this in cross-validation? And one approach of this is kind of an extreme approach, and there's parts in between, is the called leave one out cross-validation. So LOO cross-validation. And the idea here is that I'm going to create, let's say I have n data points. I'm going to create n test train splits. Okay, so I'm going to call them X, and I'll just skip all the Y notation. Assume that that's in here. X train I for each for I in 1 up to in n, and this is going to be X train I is going to be X1, X2 up to Xi minus 1, Xi plus 1 up to Xn. Okay, and so this will be then I will have X test I is just going to be Xi, right? And also the Y terms as well. Okay, so I'm creating n minus 1 points into the training set as much as I possibly can. I leave one out of the test set, but I do this for every value I. So now I have n of these training sets and n of these test sets, right? So now I'm going to have X train 1, right? X train 2 up to X train n, okay? And now I can evaluate using the test set for each of these, and I can take the average. Okay, so what this will do, it'll be my error is going to be the sum over I, right? Or the based on a the yi minus the model that's built on the training set I, which is everything except the ith point evaluated on xi. Okay, and say squared here, right? Okay, so the key thing is, so I have to build. I build a model MX train I for each kind of split. So every split, I build a new model on n minus 1 of the data points, and then I test it on just a single data point, right? So I'm going to have then a single test point per so per model here. Okay, so my training data is almost the full data, as close as I can do while holding out something to test on. I'm only testing on 1 point, but I'm averaging this over building n different of these models, right? So this I is up to n, and so for each model, I'm doing this evaluation. And so this is leveraging as much data as I can into the training. So this, if n is really big, then this takes a long time because I have to train n different models, And so this is slower, and I typically wouldn't want to do this if n was big. If I had enough data, one test train split should be fine. But if n was small, well, then it doesn't cost as long to build n of these different models. So I can do this. And I can do this to kind of evaluate how well it works, or to choose a model parameter. It's kind of tricky. Once I chose a model parameter, if I didn't have a lot of data, probably what I would do is I'd go back and use that model parameter to build on all the data, not even anything held out. Because now I have n different models here. Which one do I choose? I don't choose which one did best on their held out test point, because that wouldn't be very, that's not a lot of, that's one data point I evaluated. It's better off to go back and say, let's try training with that model parameter on all the data. That's probably what I would do in this case, but that's kind of a little bit nebulous. This is good for evaluating how well you're going to do when you don't have a lot of data. I can also say do 10 test train splits. Split the data into 10 pieces and always use 9 out of 10 of the pieces and use one of the pieces to evaluate. So there's kind of stuff like this in between where I split into different batches and I get a better evaluation across multiple builds of the model. Okay, great. So we'll do some review, and I'll probably talk about stuff beyond overfitting, some new views from maybe deep learning on Thursday, and maybe why this is the right stuff. I'll plan some fun stuff to talk about Thursday, and then we'll have the quiz. Okay, and take a look at the homework. Don't wait till the last minute to get started on this one.